Thank you very much. Hello, everyone. First of all, I would like to thank Adrian and the organizers for this nice invitation. So today, I would like to talk about the enhanced interactions of interlayer excitons in freestanding heterobilayers. So in a twisted or in a 2D heterostructure, an interlayer exciton can be formed with electron and holes sitting on different layers. So those kind of interlayer excitons, they have shown vertical dipole. So those kind of vertical dipoles will show a very strong and long-range dipole interaction. So those kind of strong Coulomb interactions can drive the whole system into different quantum phases. On the other hand, when we have a twist heterobilayer, the periodic Maury potential can also modulate the dynamics of those kind of interlayer excitons. So those kind of periodic Maury potential can be influenced by the interfacial surface states. So that's why people normally need to use hexagon boron nitride to encapsulate the heterobilayer to remove the influence from the defect states. So this way, actually, the extra HBN encapsulation will introduce a larger amount of dielectric screening to the system. So this dielectric screening can influence the dipolar interactions. So that's why people also can see the interlayer excitons at a very low temperature, like cryogenic temperature. So actually, we have another way to avoid this type of dielectric screening. At the same time, we can avoid this kind of interfacial states. So we can make freestanding heterobilayer structure. So in this platform, we can reduce the dielectric screening. This platform might provide a good system to look at the intrinsic dynamics of those interlayer excitons. So what we did here, we used lithography to fabricate micro holes in the substrate, and then we can transfer a heterobilayer structure across the micro holes. Then we can make this kind of freestanding heterobilayer structure. Then we use photoluminescence to probe the PO emission. So from this PO spectrum measured at room temperature, we can clearly see the emission from the intralayer excitons from the monolayers. At the same time, we can see a clear peak at the low energy peak. This is attributed to the interlayer exciton emission from this type 2 heterostructure. So this peak was only observed from the freestanding samples, and then this peak didn't show up from the samples that are sitting on the silicon dioxide substrate. If we look at this peak in detail, then this broad peak can be fitted by three peaks, IX1, IX2, and IX3. So in order to figure out the origin of those the three peaks, then we run a temperature-dependent photoluminescence measurement. So when we cool down the sample from room temperature all the way down to 83 Kelvin, so we can see that this interlayer exciton peak increased dramatically when we decrease the temperature. On the other hand, the intralayer exciton peak will the intensity will drop dramatically. So that's why at low temperature, this interlayer exciton peak became dominant in the PO spectrum. This PO peak matches very well with the previous report. The peak it could be from the Maury-trapped interlayer exciton in this heterobilayer structure. So based on this temperature-dependent measurement, we can assign the origin of those three peaks. So to be the Maury-trapped interlayer excitons at room temperature. IX1 and IX2 are excitons trapped in at this position, and the IX3 is coming from the interlayer exciton trapped in the second trap in the system. So IX1 and IX2 are caused by the spin orbital splitting from the WS2 layer here. As I mentioned earlier, at room temperature, we can only see the interlayer exciton emission from the suspended sample area. But when we cool down the sample, we can still see the PO emission from the interlayer excitons from the supported sample at low temperature. But the intensity was very much lower than that from the freestanding sample. So in order to look at the to compare between those two systems, we define a parameter here, beta. Beta is the intensity ratio from the intensity ratio of the interlayer exciton emission and the intralayer exciton emission. So this beta value can exclude the collection efficiency, so in the system. So from this chart, we can clearly see that the beta value from the freestanding sample was much higher than that from the supported sample. So this suggests that the freestanding sample will give us a much higher formation efficiency of the interlayer exciton. This could be caused by the reduced dielectric screening from the freestanding sample. So in order to confirm this one, we also fabricate different types of samples with different dielectric screening. So in this chart, this is the beta value. This is the different samples. For example, here, this is freestanding sample. So E, that's the sample encapsulated by two HBN layers on the top and bottom. So this one, C, is the sample sitting on silicon dioxide substrate. So from this chart, we can clearly see that when we reduce the dielectric screening, then the beta value will increase dramatically. So this further confirms that the lower dielectric screening will introduce much higher formation efficiency of the interlayer exons in the system. So this is consistent with some theoretical calculation, because when we reduce the dielectric screening, the electron and the hole, the wave function will produce larger overlap. This will introduce much larger chance for the transition of the between the electron and the holes. And also, here, I would like to summarize the three factors that can influence the formation efficiency of interlayer excitons. Previously, people report that the twist angle and also temperature can affect the formation efficiency. So when the twist angle is close to 0 or 60 degrees, then that will give you the maximum formation efficiency because of the momentum matching in the K-space. So when the temperature is lower, then that will also give you a higher formation efficiency. So here we introduce the third knob, the dielectric screening. We demonstrate that the dielectric screening can play a very important role for the formation of the interlayer exciton. So this is very important. So if you want to, previously, as I mentioned, people always need to cool down the sample to cryogenic temperature to see the interlayer excitons. But now if you want to raise the temperature, then you need to optimize the other two parameters. So that's what we did here. So we fabricate a series of freestanding samples with different twist angle. So for freestanding sample, which means the dielectric screening is reduced. So now if we reduce the twist angle, then you can see here, this is the threshold temperature from which we can see the interlayer exciton. This threshold temperature will raise from around 83 Kelvin all the way up to room temperature. So that's why from the freestanding twisted heterostructure with a twist angle of 0, then we can observe this kind of more trapped interlayer excitons at room temperature. So that was the first time for us to see this kind of multiple more trapped interlayer exciton at room temperature. Also, as I mentioned, this kind of freestanding sample will provide a very interesting platform to look at the intrinsic dynamics of the interlayer exciton interaction. So in this kind of dipolar system, exciton system, if we look at the interaction between those two interlayer excitons, you can see here when those two interlayer excitons are far away from each other, then this kind of repulsive dipole interaction will be dominant in the system. So that's why you can see the average energy in the system will be positive. Now, if we reduce the distance between those two excitons, then you can see a blue shift of the average energy in the system. Now, when those two particles are close to each other enough, then this kind of attractive exchange interaction will become dominant, and then this will bring down the whole energy of the system from positive to the negative point. So at this point, then those two interlayer excitons can bind together to form an interlayer bi-exciton state. So actually, this interlayer bi-exciton state was predicted decades ago, but it was never reported or observed in experiment in the past decades. So the reason is, if we look at this phase chart, so this is a D. D is the interlayer distance. So if we want to see the interlayer bi-exciton state, the D value needs to be small. So here, the D needs to be smaller than the average size of the interlayer exciton. So that's why in past decade, people didn't see this kind of interlayer bi-exciton from this kind of coupled quantum well structure, because it was very hard to make the interlayer distance in the quantum well structure to be small as this size of the interlayer exciton. So that's why the interlayer, this kind of atomic thin heterostructure would provide a very nice platform to look at this kind of interlayer bi-exciton phase. So previously, people didn't see this interlayer bi-exciton phase. One possible reason is people need to use HBN to encapsulate the heterostructure. So that kind of dielectric screening can prevent this kind of Coulomb interaction. So in our freestanding sample, this might be a good platform to look at this interlayer bi-exciton phase. So before I show you the experimental data, let's look at the dipole-dipole interaction from the sample 1 with a twist angle of 0. So we use this kind of power-dependent PO to look at the dipole-dipole interaction in the system. When we increase the pumping, the exciton density, we can clearly see that the peak energy will show a blue shift. This is because of the repulsive interaction. So from the supported sample, this blue shift can be fitted very well with the a model without considering the correlation between the excitons. But from the freestanding sample area, we can clearly see this blue shift shows this kind of nonlinear behavior. At this low energy, low density regime, this part can be fitted with the a model without the correlation. But in this area, it can very well modeled with the, we need to consider the pair correlation between the interlayer exciton state. So if you want to look at the dynamics of the interlayer exciton interaction, the exciton density is very important. This density is determined by two parameters: the pumping power, if we use a CW pulse laser, and also the lifetime of the interlayer exciton. So considering the damage threshold, we cannot increase the pumping power for too much. Then this lifetime could be a very important knob to play with. So as we know, if the twist angle is close to 0, then the lifetime is small. But if we increase the twist angle, this lifetime can be increased by 1 to 2 orders of magnitude. But there's a trade-off. As I mentioned earlier, if you increase the twist angle, then the PO intensity will drop dramatically. So that's why from those kind of largely twisted sample, people cannot see the PO signal at all. But now, in our case, if we can we can make the sample freestanding, we can introduce the third knob to play with. So that's why, even from the largely twisted sample, we can still see the PO emission from those samples when we make them freestanding. So from this sample 2, with a twist angle of 45 degrees, we can clearly see the interlayer exciton emission at around 83 Kelvin. Now, from this power-dependent measurement, we can clearly see when we use a low power, we can only see one peak. But now, when we increase the pumping power, we can clearly see a low energy peak will emerge and become dominant in the PO spectrum. So this peak, we named it as IXX. Actually, it was assigned to be coming from the interlayer bi-exciton state. So this assignment was supported by 4 signatures. I would like to share with you. So the first signature is the superlinear power dependence. So this peak shows this kind of superlinear power dependence, but for the other IX1 and IX2, they show this kind of linear power dependence. The second signature is the line width of the peak. So this line width, the line width of this peak is much broader than the other peaks. So this is one signature of the interlayer bi-exciton, because those kind of excitons will show much larger size. The third signature I would like to share with you is the blue shift. So when we increase the pumping power, you can see here for IX1 and IX2, those 2 peaks only show this kind of repulsive or only blue shift. But for the for this IXX peak, it shows a blue shift and then followed by a large amount of attractive or blue or red shift. So this was the first time to see this kind of attractive or red shift of the interlayer exciton. So this suggests that this peak is different from those 2 peaks. And also based on the the theoretical calculation, the binding energy of the interlayer biaxial state was calculated to be around 15 millieV. So that matches very well with what we measured from experiments about the binding energy of the interlayer exciton state. So from those, we can conclude that we firstly discovered this kind of interlayer biaxial state from the freestanding heterostructure. Now I would like to summarize my talk. Here I show you that when we reduce the dielectric screening, we can increase the formation efficiency of the interlayer biaxial state, interlayer exciton state. And also this kind of freestanding structure will allow us to look at the strongly correlated interlayer excitons and allow us to look at this interlayer biaxial state in the experiment. Finally, I would like to acknowledge my students, my collaborators, and also funding agency. Thank you very much for your attention. Thank you.
Thank you for the nice talk. Questions?
Just a quick question. You didn't describe very much the geometry of your trenches.
Okay.
How large are they in diameter and how deep?
That's good. That's a very nice question. So for the trench, the diameter was around 6 microns for this specific device. The depth was around 3 microns.
Other questions? So I have also a question about the geometry. Yeah. I might expect that at geometries like this, that you have a significant amount of strain that's present. Is this present? Is this a concern?
Yeah, that's a very good question. Yes, this freestanding structure, there might some strain, but we actually mapped the Raman. We did a Raman mapping to track the Raman peak from those monolayer structure. So based on the Raman mapping, the extracted strain in the system is very limited. So the strain can only modulate the peak position by less than 1 millieV. So that the strain can be ignored. So those peak shift has nothing to do with the strain. So we already exclude this effect from experiment.
Okay, thank you.
Thank you.
Thanks a lot for the nice talk.
Thank you.
I have a question regarding this distance argument. So you said, so you showed this exciton phase diagram, and you said this pi exciton is very stable for this, like the region of 1 Bohr.
Yeah.
And 1 Bohr radius is like 2 angstroms, I guess.
Sorry.
So I wondered, like, what is the distance between your team D layers, and does this relate to this phase diagram?
This one?
Yes. Yeah. Why is this system especially suited to have these like small interlayer distances?
Oh, okay. That's a very good question. So I just cite the result from those 2 papers. They did a theoretical calculation. So the reason could be if the space is large enough, then that will affect the Coulomb interaction between those 2 dipoles. That could be the reason, I think. But if you want to know the details, I would suggest you to read those 2 theoretical papers. Then they show this kind of detailed analysis why the D is critical to show this kind of interlayer biaxial state. Yeah.
The question is why the A, he thinks the AB star there is the real Bohr radius. It's not the real Bohr radius. It's the what the charge sees in each layer.
This is the radius of the interlayer star.
Yeah. Okay.
Yeah.
Yeah, that solves it. Thank you.
Thank you.
Thank you for nice presentation. You checked, you look at mostly the tungsten, sulfide tungsten selenide.
Tungsten, yeah, WS2 and WSE2, yes.
Yeah, did you have a chance to look other, let's say, tungsten, selenide, molybdenum selenide?
That's a good question. We actually, in the experiment, we didn't have a chance to look at those other materials yet. So to be honest, it's not that easy to make this kind of freestanding sample. So the chance was a bit low. So if you want to make a 1-layer freestanding sample, it really depends on luck. Not all my students can make this kind of freestanding heterostructure. So if you want to introduce another layer, the success rate will drop dramatically. So it takes time to make this kind of freestanding heterobilayer structure. Yeah. So that's a good question. We will work on that to look at some other systems as well, yeah, in the future. Thanks.